Your eyes are open right now, pointed at a screen, and somewhere above you, through the ceiling, through the atmosphere, through the cold indifferent dark, there are 400 billion stars in this galaxy alone, none of which know you exist. That is not a poetic observation. That is a scientific fact, and it should disturb you far more than it probably does. Richard Feynman used to say that the first step toward real understanding is the willingness to feel genuinely lost, not the comfortable kind of lost like misplacing your keys. The vertiginous, stomach-dropping kind of lost, where the ground you thought was solid turns out to be a thin crust floating over an abyss of unknowns. And when it came to the nature of reality itself, when it came to what the universe actually is underneath the familiar wallpaper of tables and chairs and solid-looking things, he was not exaggerating. What if everything you call real, every surface you have ever touched, every face you have ever loved, every moment of certainty you have ever felt, is built on something so strange and so fundamentally unlike your intuitions that calling it real is almost a courtesy we extend to ourselves so we can sleep at night? A verse, stay with that, because this is not philosophy dressed up in scientific clothing. This is the opposite. This is science arriving at conclusions so shocking that philosophy had to scramble to keep up. And if you leave before this is over, before the picture becomes complete, you will walk away with the half-understanding that is actually more dangerous than no understanding at all. The person who knows nothing about quantum mechanics and the nature of reality at least has the humility of ignorance. The person who half knows tends to wave it away as abstract, as something that does not affect their life. But it does, profoundly. And Feynman spent decades trying to explain exactly why, so let us begin where he always began. Not in a laboratory, not with equations, but with a scene so ordinary it almost embarrasses the enormity of what it contains. Picture someone standing in a dark backyard on a clear night, somewhere far enough from city lights that the Milky Way is visible. Not the smudged suggestion of stars that most people see, but the real thing, that river of light that is actually the disk of the galaxy seen from inside, edge on, like looking at a plate from the rim. The person standing there feels something they probably cannot name. A kind of awe mixed with unease, a sense of scale that the human nervous system was simply not designed to process comfortably. And here's where Feynman would lean forward, eyes bright, and say, good, that discomfort is the beginning of honesty. Because what that person is seeing with their perfectly ordinary human eyes is not the universe as it is. It is a portrait of the universe as it was, painted in ancient light, some of it millions of years old, some of it from stars that no longer exist. The star they are looking at right now, with their retina doing its faithful biological job, might have exploded 600 years ago. That light left before anyone on Earth had heard of the Americas, and it is only arriving now, closing the last centimeters of a journey across a distance so enormous that the number of kilometers required to express it is essentially meaningless to the human brain. Pews, and that is just the visible part. Now here's where the real trouble starts. And I want you to notice that I said real trouble because what comes next is not a metaphor. It is not a poetic flourish. It is the conclusion that the most rigorous, most tested, most predictably successful physical theory ever produced by human civilization forces us to accept about the nature of everything we see and touch. If you have ever heard someone say that atoms are mostly empty space, you have heard a version of this idea, a simplified version that still manages to make people uncomfortable at cocktail parties. The truth is considerably stranger because empty space is not really empty either. And the line between the atom and the void around it, the boundary between matter and nothing, is not a clean line at all. It is a blur, a probability, a cloud of potentiality that only resolves into something definite when something else interacts with it. Feynman did not just teach quantum mechanics. He felt it in a way that was almost personal, almost passionate. He used to say that nobody understands quantum mechanics, and he meant it as an honest confession, not a dismissal. He meant that the mathematical machinery works with breathtaking precision, predicts experimental outcomes to 11 decimal places, forms the foundation of every transistor in every device you have ever used, and yet the picture it paints of what is actually happening underneath is so alien to Human intuition that even the people who spend their lives calculating with it cannot fully visualize it without feeling the ground shift. So let us talk about what quantum mechanics actually says, stripped of the mystical language that tends to surround it in popular culture, stripped of the wishful thinking and presented the way Feynman would want it presented, with radical honesty and genuine delight at the strangeness. Here's the core claim, and it is verified to a degree of precision that makes it as solid a fact as any in human knowledge. Before a particle is observed or measured, before it interacts with anything in its environment, it does not have a definite position. It does not have a definite speed. It does not have a definite spin. It exists as a superposition of multiple possibilities simultaneously, described by a mathematical object called a wave function, which encodes the probabilities of finding it in various states when measured. The particle is not hiding its position from us, like a playing card face down on a table. The position does not exist as a definite thing until the measurement happens. Espera, because this is where people want to say, but surely the card had a value before we turned it over. Surely the particle had a position before we looked. And this is precisely what experiments have ruled out. The Bell test experiments, first proposed by the physicist John Bell in the mid-20th century and then carried out with increasing precision over the following decades, tested exactly this question. They asked, is the particle secretly carrying a hidden definite value that we just cannot see? Or does the definite value genuinely not exist until measurement? And the answer that the universe returned unambiguously, repeatedly, across laboratories around the world, is that the definite value genuinely does not exist beforehand. The property is created, in a real sense, by the act of measurement itself. Now, in a moment, the reason this applies not just to electrons in a laboratory, but to the table in front of you, to the planet under your feet, to your own body, will become something you genuinely cannot unfeel. But first, let me tell you something that makes the whole thing even stranger. The wave function, that mathematical description of all the possibilities, can spread across space. It can be in principle simultaneously in multiple places. And when two particles interact, their wave functions become entangled, meaning the mathematical description of one cannot be written separately from the other. Measure one particle and you instantly affect what you will find when you measure the other, regardless of how far apart they are. Feynman used to describe this with barely contained glee as the thing that bothered Einstein so much that he spent the last decades of his life trying to argue it could not be real. Einstein called it spooky action at a distance. He thought it revealed a flaw in the theory. The experiments proved Einstein wrong. Not gently wrong, not wrong in a minor technical detail, but wrong about something he considered philosophically essential, that reality is local, that distant things cannot instantly affect each other, that there are no hidden threads connecting separated parts of the universe. Those threads exist. They are called entanglement, and they are real. And they operate at a level so fundamental that they are woven into the fabric of what the universe is made of. Bueno! And now here's the part that Feynman considered the most astonishing, the part that turns the discussion from an abstract physics lecture into something that reaches into the meaning of your existence. If particles do not have definite properties until they interact, and if everything you can see, touch, taste, and smell is made of particles, then what does that say about the reality of the things you perceive? The table is made of atoms. The atoms are made of protons, neutrons, electrons. Those particles are governed by quantum mechanics. At the level of the quantum, the table is not a solid, definite, located thing. It is an astronomically complex web of interacting probability distributions, which collectively behave in ways that our macroscopic senses interpret as solidity, color, texture, weight. The solidity is real in a practical sense. You will not fall through the floor. But the floor is not what you think it is. Deixem pensar un momento. Because the question that naturally arises is, if quantum effects are real at the particle level but do not seem to show up in our everyday experience of solid tables and reliable chairs, why not? Why does the quantum strangeness not invade the macroscopic world? And the answer is decoherence. When a quantum system interacts with its environment, with the air molecules around it, with the photons bouncing off it, with everything it is in contact with, The superposition of possibilities does not disappear, but it becomes entangled with an enormous number of other particles in an effectively irreversible way. The different possible states become correlated with different states of the environment in a way that makes them practically impossible to distinguish or recombine. The quantum weirdness does not vanish. It becomes diluted into the environment so thoroughly that we cannot detect it at the scale we operate on. The table looks solid because the quantum possibilities for its trillions of constituent particles have decohered into a stable classical-looking configuration through their constant interaction with everything around them. But here's what Feynman would want you to sit with, what he would want you to take out of the laboratory and into your actual life. The process of decoherence is a process of information spreading. The reason the table looks definite is not that the table is made of something definite. It is that the quantum information about the table state has become distributed across the environment in a way that, for all practical purposes, forces a single outcome from our perspective. Our perception of a definite, solid, located world is, in a very deep sense, a consequence of our relationship to the environment, not a direct window into some underlying solid reality. Now, there are serious, brilliant physicists who would want to qualify that statement, who would say that decoherence explains the appearance of classical reality without fully answering the deeper question of why we experience one outcome rather than another. And they are right to want that qualification. This is the measurement problem, the deepest open wound in the foundations of quantum mechanics, and it has not been healed. And this is the part where Feynman would laugh, that slightly mischievous laugh, and say, see, this is what makes it interesting. Because the fact that we do not know is not a failure. It is an invitation. It is the universe leaving a door ajar and daring you to push it open. Avere, let us take this a step further, because we have been circling something that needs to be named directly. If you want to stay, and I think you do, because what is waiting on the other side of this is one of the most beautiful and terrifying ideas in all of human thought, then hold on to this thread. The quantum description of reality is not just strange in the laboratory. It has direct consequences for how we understand time, causality, the past, the future, and even the idea of identity. Let us pull on each of those. First, time. In quantum mechanics, the wave function evolves deterministically according to the Schrödinger equation. That evolution is perfectly smooth, perfectly reversible, perfectly symmetric. With respect to time, there is no arrow of time built into the fundamental quantum equations. The distinction between past and future, the overwhelming sense that time flows in one direction, that the past is fixed and the future is open, is not contained in the basic laws. It emerges from statistical mechanics, from the fact that the universe started in an extraordinarily low entropy state and has been moving toward higher entropy ever since, which gives rise to the thermodynamic arrow of time that governs our experience. But the fundamental equations do not care. At the quantum level, time is not a river flowing in one direction. It is something far more geometrical, far more neutral than that. Feynman himself contributed one of the most mind-bending ideas in this territory, his path integral formulation of quantum mechanics. Instead of describing a particle as following a single definite trajectory from one point to another, Feynman showed mathematically that the behavior of a quantum particle can be calculated by summing over all possible paths it could take simultaneously, including paths that go backward in time, paths that take absurd detours through distant corners of the universe, paths that violate every intuition about how objects move. Every possible path contributes to the final outcome, weighted by a factor that depends on the path's properties. The particle, in a real mathematical sense, takes all paths at once. When a colleague once sat next to Feynman on an airplane and asked what he was working on, Feynman said, "An electron goes from here to there by exploring every conceivable route through the entire history of the universe, and the one we observe is the sum of all of them." The colleague stared out the window for a long time. That story, whether precisely true or not, captures something essential about Feynman's way of explaining physics. He wanted the strangeness to land. He did not want you to nod politely and move on. He wanted you to feel it. Pews, let us feel the next one. Causality, we experience the world as a chain of causes and effects. One thing happens, it causes another thing, which causes another thing. This sequence feels absolute, foundational, the scaffolding of logic. And quantum mechanics does not quite destroy this picture, but it does complicate it in a way that has kept philosophers employed for a century. Consider the double-slit experiment. A particle, an electron, is fired at a barrier with two slits in it. On the other side of the barrier is a detector screen. If you fire many electrons and do not measure which slit each one goes through, they create an interference pattern on the screen, exactly the pattern you would expect from waves passing through both slits simultaneously and interfering with each other. This tells you the electron went through both slits at once. When you add a detector to measure which slit the electron goes through, the interference pattern disappears. Knowing which slit the electron used destroys the interference. Here's the part that seems to involve causality running backward. In some variations of this experiment, the choice of whether to measure which path the particle took can be made after the particle has already hit the detector screen in what is called a delayed choice experiment. The results are consistent with the particle having somehow adjusted its behavior in the past based on a measurement decision made in the future. Now, this does not mean information travels backward in time in a way you could exploit to change history. But it does mean that our intuitive picture of a definite past, a fixed sequence of events marching forward, is not the full story. The universe appears to be, in some sense, writing its history only as it is read. Feynman would pause here, look directly at you and say, "Now, do you see why I told you nobody understands this? Not because the math is unclear, the math is beautiful, but because the picture the math forces us to paint of reality is one that our brains, evolved to track predators on a savanna, simply did not prepare us to visualize." And this is where the Fermi paradox enters the room and the temperature drops. Because if reality is this strange, if the universe operates on principles so far beyond our everyday intuitions, then what does that imply about our search for other intelligence in the cosmos? What does it imply about our ability to recognize it, communicate with it, or survive the medium? The Fermi paradox, for those who have not felt its particular sting, is this. The universe is roughly 13.8 billion years old. Our galaxy alone contains hundreds of billions of stars, many of which are far older than our sun, many of which have planets in orbitable zones. The conditions for life as we know it are not rare in any meaningful sense. The chemistry of life uses carbon, hydrogen, oxygen, nitrogen elements that are among the most abundant in the cosmos. Given the numbers, given the age of the universe, given the sheer number of potential sites for life, there should be civilizations out there vastly older than ours. Some of them should have had millions of years to develop. Some of them should be visible. Some of them should be here. And yet, silence. The sky is quiet. The radio spectrum is quiet. The optical spectrum is quiet. We have been listening for decades and heard nothing that unambiguously points to intelligence beyond Earth. Now, Feynman did not live to see the most sophisticated phase of this search, but his way of thinking about it is exactly what is needed, because the Fermi paradox is not just an astronomical puzzle, it is a window into something far darker. Something that, if you let yourself look through it honestly, should change how you think about the future of human civilization. The Great Filter is the name given to whatever process or set of processes makes intelligent spacefaring civilization so rare as to be effectively invisible. The question is where the filter sits. Is it behind us? Is it in our past? In the emergence of life? Or in the development of complex cells? Or in the leap to multicellular organisms, all of which seem to have been extraordinarily unlikely events, events that might have happened only once in the history of this galaxy? If the filter is behind us, then we are perhaps the winners of a cosmic lottery so unlikely that we are genuinely alone or nearly alone. And the silence is simply the silence of a universe where intelligence almost never ignites. Or is the filter ahead of us? Is there something that civilizations do to themselves when they reach a certain level of technological power? Something that almost every civilization that gets that far does. Something that ends them before they can spread to the stars. Nuclear weapons arrived on Earth before any serious framework for managing them. Biological engineering is advancing faster than any international treaty structure can keep pace with. Artificial intelligence is developing in ways that even its creators cannot fully predict. Climate destabilization is a process we initiated before we understood what we were initiating. The list of ways a technologically capable civilization might end itself is not short. And here's the thought that Feynman would find most troubling, the one that sits at the intersection of quantum physics and the Fermi paradox in a way that almost nobody talks about. If the nature of reality is as strange as quantum mechanics shows it to be, if the universe is fundamentally probabilistic, if the distinction between possible outcomes and actual outcomes is blurrier than our intuitions suggest, then the question of which outcomes actually occur, of which branch of possibility the universe actually follows, may depend in ways we do not understand on what intelligent observers do. This is not mysticism. This is the honest frontier of the measurement problem in quantum mechanics, extended to its logical boundaries. We do not know what role, if any, observation and information processing play in the actualization of physical reality. We do not know whether a universe with no observers in it is in some sense different from a universe with observers. These are open questions, not settled ones. And if intelligence is rare, if observers are rare, the universe loses something in a way that is hard to describe but impossible to dismiss once you have felt it. Now, in a moment, everything that has felt like darkness in this conversation is going to turn around, because Feynman's genius was never in the darkness for its own sake. He went into the dark because that is where the honest things live, and then he brought them back into the light. But first, the counterexample that breaks the comfortable assumption that understanding all of this is only for experts. Consider a student, a young woman in an introductory physics course who is performing brilliantly on every written exam. Perfect scores, clear understanding of the math. The professor would look at her answers and feel proud of what he saw. From the outside, she was the picture of a student who had understood everything. And then one day after class, she stayed behind and said to the professor, "I can do every problem you give me, but I have no idea what any of it means. I feel like I'm translating a language I have memorized without ever learning to speak it." The professor told her that this was in fact a sign of genuine understanding, because she had identified the exact problem that Feynman spent a career trying to solve: the gap between computing and comprehending, between manipulating symbols and actually knowing what they point to change. She had looked perfectly capable on the outside and was completely lost on the inside. And the professor told her, "Welcome to the club. Nobody has fully solved this. You're not behind. You're at the frontier." That gap between the appearance of understanding and the actual texture of knowing is what Feynman considered the central danger in science education. He called it cargo cult science, a phenomenon where the forms of scientific thinking are imitated without the substance, where people wear the costume of rigor without doing the actual uncomfortable work of confronting what is genuinely not understood. And this applies directly to how most people relate to the question of reality. The word quantum gets attached to everything from skin cream to motivational seminars, and almost none of it has anything to do with the actual content of quantum mechanics, which is, I remind you, the most precisely confirmed physical theory in the history of science, and which says things about reality that are deeply, seriously strange in ways that cannot be papered over with inspiring language. The appearance of understanding is not understanding, and the stakes of the confusion are high, because here's what quantum mechanics actually implies for your relationship to reality, stated as plainly as Feynman would want it stated. The objects you interact with every day are not solid in the way you think they are. They are stable configurations of probability clouds, held in recognizable shapes by quantum electrodynamic forces, and the solidity you feel when you press your hand against a table is the electromagnetic repulsion between the electrons in your hand and the electrons in the table. You never actually touch anything in the classical sense. The atoms do not merge. What you feel as touch is the force of repulsion between charged particles. The colors you see are not properties of objects in the world. They are properties of your visual system's response to specific wavelengths of electromagnetic radiation. The world outside your head does not have colors. It has photons of various energies. Your brain constructs the experience of redness or blueness from the signals sent by the cone cells in your retina. The red of a sunset is a creation of your nervous system, not a fact about the sky. The continuity of your experience, the sense that there is a single you moving through time, observing things from moment to moment, is a construction of your brain, assembled from the massively parallel processing of sensory information, memory, and predictive modeling, stitched together into a narrative that feels seamless but is, upon close inspection, riddled with gaps, delays, and confabulations. Your brain receives sensory information and then, several hundred milliseconds later, presents it to your consciousness as if it arrived instantly. The present moment you experience is already the past. These are not interpretations. These are the findings of neuroscience, quantum physics, and the philosophy of mind, converging on a picture of reality that is simultaneously more wonderful and more vertiginous than the common-sense picture we walk around with. Feynman used to say, when you get as far out as quantum mechanics, you have to be willing to give up a lot of what seemed obvious. Not because the universe is trying to confuse you, but because the universe has no obligation to be obvious. It is what it is, and the job of the scientist is to find out what that is, regardless of whether it fits our intuition. Aver. So now let us talk about what this means, concretely, for how you live, for how you think, for how you understand your own place in this cosmos that is simultaneously 400 billion stars wide and smaller than an atom at the level where its real rules operate. First tool, calibrated uncertainty. One of the things quantum mechanics teaches, at a philosophical level, is that our intuitive assignment of probabilities to events is often deeply wrong. We are overconfident about what we know and underconfident about what we do not. The universe, at the fundamental level, is probabilistic. Our certainties are approximations. The appropriate response to this is not paralysis or nihilism. It is the cultivation of what Feynman called the pleasure of finding things out, the willingness to hold beliefs with a degree of confidence proportional to the evidence and to update them when new evidence arrives without defensiveness, without ego, without the need to have been right. Second tool, the distinction between the map and the territory. Every model of reality, every theory, every scientific framework is a map. The map is not the territory. Quantum mechanics is a map, an extraordinarily good one, but still a map. It may be superseded, extended, or reinterpreted. What it describes may be a projection of something even stranger that we have not yet conceived. Holding your models as maps rather than as reality itself is the epistemological habit that keeps you honest, keeps you curious, and keeps you from the kind of brittle certainty that breaks when the evidence shifts. Third tool, the appreciation of scales. One of the most disorienting things about quantum mechanics is that it operates at a scale so far below our everyday experience that we have no direct intuition for it. An atom is to a meter what a marble is to the distance from Earth to the moon. A proton is to an atom what a flea is to a city. The scale at which quantum effects are directly relevant is so small that the fact that quantum mechanics controls the behavior of your coffee cup, your bones, your thoughts is genuinely astonishing. Learning to hold multiple scales of reality in mind simultaneously, the quantum and the classical, the cellular and the astronomical, is one of the most powerful cognitive skills a person can develop. Now here's the piece that connects the quantum strangeness to the Fermi paradox in a way that I find in Feynman's spirit genuinely thrilling. The emergence of life and then of intelligence on a planet like Earth required the quantum mechanical behavior of chemistry. The formation of DNA, the folding of proteins, the capture of photons by chlorophyll and photosynthesis. All of these processes depend on quantum effects at the molecular level. In fact, quantum tunneling, the ability of particles to pass through energy barriers that classical mechanics says they should not be able to cross, is essential to the chemistry of life. Enzyme catalysis, DNA mutation, possibly even the initial steps of photosynthesis, all of these involve quantum tunneling in ways that are actively being researched. This means that life, and therefore intelligence, and therefore the capacity to ask questions about the nature of reality, is a quantum phenomenon. The universe generated its own self-examination through quantum processes. The fact that a pattern of atoms organized by quantum chemistry can sit in a dark backyard and wonder what the stars are made of, and then actually find out, is perhaps the most extraordinary fact about the cosmos that we know of. Feynman felt this with something that in another person you might call reverence. He was not religious in any conventional sense, but he had what he described as a feeling of awe when contemplating the natural world that was, he said, more satisfying than any theology he had encountered, because it was about something real. He told a story once about sitting with an artist friend who showed him a painting of a flower and said that scientists, by analyzing the flower, rob it of its beauty, and Feynman disagreed firmly and passionately. He said that the beauty of the flower as seen with the eye is the beginning, not the end. That knowing about the cells and about the molecules in those cells and about the quantum processes that make the pigments absorb specific wavelengths of light and reflect others does not diminish the beauty. It multiplies it, it adds layers of beauty that the eye alone cannot access. And he was right. The blue of the sky is not just blue. It is the result of Rayleigh scattering of photons bouncing off nitrogen and oxygen molecules at angles that depend on their wavelength. Shorter wavelengths scattered more, which is why the sky is blue and not red in daytime. That process is quantum mechanical at its core. The blue is a quantum effect writ large across the atmosphere, and the fact that your eye and brain render it as blue is a neuroscientific fact about how information is processed by living matter. The sky is beautiful, and the sky is strange, and the sky is scientifically miraculous, all simultaneously losing the capacity for this kind of layered wonder. This Feynman called a tragedy. Not a personal failure, not a matter of taste, but a genuine loss. Because the ability to be astonished by the real universe, rather than a simplified version of it, is the ability to be in honest contact with what actually exists. And being in honest contact with what actually exists is, in the long run, the only reliable basis for making good decisions individually and as a civilization. Pews now let us return to the Fermi paradox and the Great Filter, because this is where everything becomes urgent. If the universe is as old as it is, and if the conditions for life are as common as they appear to be, and if intelligence has arisen at least once, then the question of why we do not see other civilizations is not merely an astronomical curiosity, it is a diagnostic tool. It is the universe trying to tell us something about our situation, and we should be listening very carefully. There are several possible answers to the Fermi paradox, and none of them are comfortable. Perhaps life itself is extraordinarily rare. The emergence of the first self-replicating molecules from non-living chemistry, the step called abiogenesis, has never been recreated in a laboratory. We do not know how it happened. The probability of it happening spontaneously may be vanishingly small, so small that it may have happened only a handful of times in the observable universe, despite the enormous number of candidate planets. Perhaps complex multicellular life is extraordinarily rare. The emergence of the eukaryotic cell, a cell with a nucleus and complex internal machinery, happened exactly once in the history of Earth, roughly 2 billion years ago, and it appears to have been the result of an extraordinarily unlikely symbiotic merger between two types of microorganisms. Without that event, complex life as we know it, and therefore intelligence, would not exist. Perhaps intelligence itself is extraordinarily rare. The evolutionary pressures that produced human-level cognition on Earth required an extremely specific sequence of environmental conditions, evolutionary pressures, and random mutations. Change any of 100 factors, and the dominant organisms on this planet might be something more like octopuses, which are remarkably intelligent but have not developed radio telescopes. Or perhaps, and this is the one that keeps people up at night, intelligence is not rare. Perhaps it arises fairly readily, and perhaps there is something that intelligent civilizations do, reliably, when they reach a certain level of technological power that ends them, not necessarily through malice. Through the simple catastrophic mismatch between the speed of technological capability and the speed of the wisdom required to use it well. Feynman had a deep worry about this, expressed not through dramatic speeches, but through the consistent emphasis he placed on intellectual honesty as a moral value. He believed that the habit of self-deception, of believing what is comfortable rather than what is true, of performing the rituals of understanding without doing the actual work, was not just an intellectual failing, it was a danger. Because civilizations that lose touch with truth lose the ability to correct their own errors. And a civilization that cannot correct its errors once it has the power to make errors of civilizational scale is a civilization that will not last. The silence of the universe may be a warning, not a message, not communication from some other intelligence. A warning that the path from fire to fusion to whatever lies beyond is narrower than we would like to believe. Now here's where Feynman would not let you leave on that note. Because despair, he would say, is just as much a failure of honesty as false optimism. The correct response to a genuine danger is not to be paralyzed by it, but to understand it as clearly as possible and then act on that understanding. And the tools for that response are, in fact, the same tools that quantum mechanics gives you. The same intellectual habits that allow you to accept that reality is stranger than your intuitions, that certainty is an approximation, that the map is not the territory, that you should update your beliefs when evidence demands it. These habits are not just good for passing physics exams, they are the cognitive architecture of a civilization that can survive its own power. The people who built the atomic bomb understood what they had made. Some of them, like Richard Feynman himself, were never quite the same afterward. He described sitting in a New York restaurant after the bombs had dropped on Japan, watching people going about their ordinary lives, eating their ordinary meals, and feeling a kind of horror at their ordinariness, because he was looking at a city and thinking, I know how to destroy all of this. I know exactly what it would take, and the knowledge did not feel like power. It felt like weight, but it also felt like responsibility. And responsibility for Feynman meant honesty. Honesty about what was known. Honesty about what was not known. Honesty about the gap between the two, which is where all the danger lives. What we know is extraordinary. The universe is 13.8 billion years old, vast beyond any intuitive comprehension, made of quantum fields whose behavior we can calculate with stunning precision, and it produced, on at least one occasion, creatures capable of asking questions about all of this. That is extraordinary. What we do not know is also extraordinary. We do not know whether we are alone. We do not know what dark matter is, even though it makes up roughly 27% of the energy content of the universe. We do not know what dark energy is, even though it makes up roughly 68%. We do not know how to reconcile quantum mechanics with general relativity into a single coherent theory of everything. We do not know what happens at the center of a black hole. We do not know why there is something rather than nothing. And right in the middle of all this not knowing is the question of what reality actually is, the question we started with. And the honest answer, the Feynman answer, is we have the most extraordinary partial picture ever assembled by any intelligence we know of, and the edges of that picture are alive with mystery. That mystery is not a defect. It is an invitation. It is the universe extending an open hand and saying, you have come this far. Your ancestors stared at the sky with no tools and no framework and nothing but curiosity, and they began the long, patient, magnificent work of figuring out what is actually going on. And now you're here, with quantum field theory and radio telescopes and the knowledge that the stars are nuclear reactors and the atoms in your body were forged inside stars that exploded before the Earth existed, and the knowledge that the fundamental particles in those atoms have no definite position until they interact, and the knowledge that two particles separated by the width of a galaxy can be correlated in ways that have no classical explanation. You're here, and the question is what you do with that. Feynman used to end his lectures not with summaries, but with images. He would leave people with a picture that contained, compressed inside it, more than any summary could hold. So let us end with one. Somewhere in the observable universe, which extends roughly 46 billion light years in every direction from the point where you're sitting right now, there may be other minds. We do not know. The silence does not tell us they are absent. The silence tells us only that we have not yet found them, or that they have not yet found us, or that the filters between simple matter and lasting intelligence are so severe that we are something rare, something precious, something that the cosmos has been building toward for nearly 14 billion years and may have produced only a handful of times. If that is true, then the capacity for wonder that Feynman embodied, the willingness to look at a flower or a star or an equation and feel genuine astonishment at what is actually there rather than what you expected to be there, is not a luxury. It is not a personality trait. It is perhaps the most important thing about us. It is what makes us, in the full scientific sense of the word, significant. Not because the universe cares about us, it does not. The universe is not structured around our comfort or our survival. But because we are the part of the universe that has turned around and looked at itself, that has asked what it is and actually made progress toward answering, that has the capacity to understand the laws that govern all of this, and therefore, at least in principle, the capacity to navigate them wisely. Losing that capacity, choosing comfort over truth, choosing the appearance of understanding over the actual work of understanding, is the only form of failure that Feynman considered genuinely tragic. Not failure at a problem, not being wrong about a theory. He was wrong about things cheerfully, productively, and he updated when the evidence demanded it. The tragedy, the real one, the one he spoke about with something close to grief, is the failure to try. The decision to close the question before it has been asked, to accept the common sense picture of reality without ever pressing against it, to find out where it gives way. The surface of reality, if you press it, gives way almost immediately. Underneath is something so much stranger and so much more beautiful that the people who have spent their lives pressing against it consistently report the same thing, that they cannot go back to the unexamined version. Not because the examined version is more comfortable. It is often less so. But because it is honest, and honest contact with the real universe, even in its most disorienting depths, is the closest thing to wisdom that human beings have found. So look at the ceiling above you right now. Above it is the sky. Above the sky is a vacuum seething with quantum fluctuations. Above that is the thermosphere, and then the interplanetary medium, and then the solar wind streaming outward from a nuclear furnace 8 light minutes away. And beyond that, the vast, mostly empty, staggeringly old, quietly mysterious galaxy in which this entire story is taking place. And you are in it? Made of atoms forged in stellar explosions, governed by quantum laws you can spend a lifetime understanding and never exhaust. Looking out at a universe that generated you and that you can, in return, describe with mathematics of extraordinary precision, that is not nothing. That is perhaps the most extraordinary fact there is. And Feynman, if he were sitting next to you right now, would lean over and say, "So what are you going to do with it?" That question is not rhetorical. It is the one that everything we have talked about today has been building toward. What do you do with the knowledge that reality is not what it appears? What do you do with the knowledge that you are a quantum event, that your certainties are approximations, that the universe is vast and old and mostly silent and probably full of dangers we have not yet learned to name? What do you do with the knowledge that the filter between simple matter and lasting intelligence may be ahead of us rather than behind us? That what we do now, with this window of capability and knowledge that our civilization has worked so hard to open, may determine whether the story continues, whether it joins the silence. You stay curious. You stay honest. You press against the surfaces of things to find out where they give way. You hold your beliefs with appropriate uncertainty. You update them when the evidence demands it. You do not mistake the map for the territory or the costume for the understanding. You look at the flower and you see the beauty the eye sees, and then you look deeper and you see the quantum chemistry and the evolutionary history and the neuroscience of color perception, and you let all of those layers of beauty add up instead of canceling each other out. And every now and then you go outside on a clear night and look up and you let yourself feel the full weight of what you're seeing. Not the comfortable version, not the postcard version, but the real version. Ancient light from objects so far away and so long dead that the numbers involved are essentially poetry, arriving at the surface of your retina, triggering a cascade of quantum mechanical processes in your visual cortex, producing the experience of a sky full of stars and a creature made of the same matter as those stars, a creature that managed against odds that are almost inexpressible to figure out what stars are made of. That is the universe examining itself, and the least we can do is take the examination seriously.